So imagine for a second that you are looking at a single real loan portfolio, like real borrowers, real money. And you walk into four different departments at this company and ask each of their teams for one basic metric, which is the default rate.
Right, just what percentage of our loans have gone bad.
Exactly. So you start with the risk team. They pull up their dashboards and tell you it's 49%, almost half the portfolio.
Wow, okay.
Yeah. Then you walk over finance, looking for a second opinion, and they tell you it's 21%. Feeling thoroughly confused at this point, you check the board of directors' latest quarterly report, and they are looking at a terrifying 72%.
That is quite the jump.
It is. And desperate for a baseline, you ask the regulatory reporting team, and they tell you the default rate is exactly 0%.
And the kicker here is that none of those teams are lying to you.
Wait, really?
Yeah, I mean, none of them made a mathematical error and nobody has a broken spreadsheet. You are getting four wildly different numbers describing the exact same underlying reality on the exact same day.
Okay, let's unpack this because it sounds like a riddle. But today we are doing a deep dive into a comprehensive technical and business document that tackles this very issue.
Yeah, it's a fascinating document.
It really is. It details a hackathon project called the Default Rate Semantic Engine, which was created by Sumit Saha, and it actually took home an honorable mention in the data analytics category. So your mission today, as the listener, is to understand how this engine solves one of the most insidious problems in modern business. Like, what happens when the exact same word means completely different things to different people?
And, before you can even attempt to write code to fix a problem like this, you have to understand the human element.
Right.
You have to figure out why those four numbers diverge so drastically. I mean, the divergence isn't just random chaos. Each team's version of the default rate makes total rational sense for the specific incentive structure their department operates under.
So if the risk team is sitting at almost 50%, what on earth are they actually measuring? Because that seems incredibly high for a functional business.
Well, they are operating as the company's early warning system. Their entire mandate is to know immediately when a loan might be souring so they can start collections.
Ah, okay.
Yeah, so because of that mandate, their definition of default is incredibly sensitive. They use a 30-day past due threshold. The moment you are 1 month late, boom, you trigger their system.
Yeah, makes sense.
And furthermore, they only look at the principal amount, entirely ignoring interest. The official rate they generate is 49.19%.
So they would rather sound the alarm on 10 loans that eventually recover on their own than, miss the one loan that actually goes entirely bad.
Precisely. Now compare that to the finance team, who is sitting at 21.31%. Finance doesn't care about early warnings. I mean, they care about the actual economic loss that hits the profit and loss statement at the end of the quarter.
Right, the actual bottom line.
Exactly. So they use a much more forgiving 90-day threshold, which is generally the point of no return for a borrower. And crucially, they look at net loss.
What does that mean in this context?
It means if a loan defaults, but the collections team manages to seize a car or recover some cash, finance subtracts that recovery amount from the total.
Which totally makes sense for the accountants, but then you walk into the boardroom and the directors are staring at a 71.70% default rate. How are they getting a number that high?
So the board operates under a highly conservative governance policy. They use a 60-day threshold. But the real driver of that 72% is a single massive blanket rule they apply. Any loan that has ever been restructured counts as defaulted forever. Forever. And restructure just means the borrower was struggling at some point, so the company modified the terms of the loan to help them out. In this specific portfolio, there are 957 restructured loans.
Oh, wow.
Yeah, so even if those borrowers have been paying perfectly on time for the last 3 years, the board counts every single one of them as a default because the original contract was broken.
And then there's the regulatory team. They claim 0%.
Right, because they aren't calculating a broad portfolio health metric at all. They are filling out a highly specific government call report. That federal report requires a 90-day threshold, principal only, and it demands a specific origination cohort filter.
Like a specific time frame.
Exactly. It asks, what is the default rate of loans originated specifically in Q3 of 2024? If you run the query without providing a specific time cohort, the system defaults to 0 by design.
It's honestly like asking four different people if a car is broken.
Oh, that's a good way to look at it.
Right. Because if you ask the mechanic, they'll say yes, because the brake pads are worn and need replacing soon. But the driver says no, because it still gets them to work every morning. The insurance adjuster says yes, because it was in a prior accident and technically holds a salvage title. And the DMV says the car doesn't even exist because you forgot to file Form 104B.
Exactly.
They are all entirely correct, just based on what they need the car to do.
That analogy hits the nail on the head, because the term default rate is carrying four entirely different meanings simultaneously. Without a semantic engine to reconcile those meanings, every stakeholder meeting turns into a useless argument. Everyone brings their own mathematically correct spreadsheet, and nobody can actually agree on the fundamental health of the business.
So we understand the psychology of why they disagree. But if we want to build a system to get them on the same page, we hit a massive roadblock.
Mhm.
They are all pulling their metrics from completely different, really messy data systems.
Yeah, you can't reconcile the math if you don't reconcile the underlying reality first.
Exactly.
And the Hackathon project solves this by introducing a three-tier data architecture. So tier one is just raw data extraction. And when we say messy enterprise data, we aren't talking about a few missing commas.
Far from it.
We are talking about data coming from legacy core banking systems, modern servicing platforms, third-party collection software, and regulatory feeds. And none of these systems were designed to talk to each other.
Yeah, the source document gives a terrifying glimpse into this chaos. Like, in the single portfolio, there are 37 different spellings for just 7 basic loan status codes.
It's wild.
You have current spelled out normally, you have cur, you have good standing shouting at you in all caps, and good standing in lowercase. Date formats are a mix of European and American standards. Boolean flags, like the simple yes or no fields, are recorded as Y, yes, a 1, or true.
Right.
The system even found 23 loans with impossible negative principal amounts and several duplicate loan IDs.
And leaving that data raw means any math you do on it is inherently flawed. That necessitates tier two, which is conformed data. The engine applies 9 strict business rules to scrub this raw chaos down to 1,953 clean conformed loans.
Okay, so it cleans house.
It does. It forcefully collapses all 37 of those status spellings into 7 standardized canonical labels. It takes any days past due metric that is somehow negative and clamps it to 0. It drops the duplicate loans entirely. But the most vital intervention is how it handles conflicts between different fields.
I want to dig into that, actually, because there's a specific rule called the status DPD conflict resolution.
Yes.
The engine found about 65 loans where the status text field literally says current, but the numeric days past due field, the DPD, says the borrower is 45 days late. The engine's programmed rule is that the days past due number always wins.
Correct.
But wait, hang on. If a human loan officer or a banking process has flagged a loan as current in the system, isn't it incredibly risky to program a piece of software to just ignore that human label and blindly trust a days past due counter instead?
What's fascinating here is the fundamental difference in reliability between a categorical label and a numeric measurement. The status field is just text. It relies on human data entry or overnight batch processing, which means it often lags behind reality.
That makes sense.
Right. But days past due is a hard, automatically calculated numeric measurement of time elapsed since the last payment cleared. It is inherently more trustworthy. By establishing a rigid programmatic rule like DPD, always overrides status, the engine achieves something critical. The pipeline becomes idempotent.
Idempotent. Let's make sure we translate that because it's a fantastic engineering concept but sounds like a medical condition.
Yeah, it does sound a bit clinical. It just means you can run the exact same raw data through this processing pipeline 10 times or 100 times, and you will get the exact same clean output every single time.
So no surprises.
Exactly. There is no randomness, no subjective human judgment calls on a case-by-case basis. If a federal auditor sits down and asks exactly how you arrived at a specific number, you need a mathematically provable, completely reproducible path from raw chaos to clean data. Idempotency guarantees that path.
Which brings us to the final step of the cleanup, Tier 3 metric-ready inputs. Once the data is perfectly conformed, the engine turns every loan into an immutable Python object. It basically freezes them.
Yeah, it locks the reality of the loan into place. Once it becomes an immutable object, no rogue piece of code later in the pipeline can accidentally overwrite a loan balance while trying to calculate a percentage. The foundation is poured and set.
Okay, our data is pristine. But we still have 4 different departments yelling at each other across the boardroom table about their specific numbers. So the semantic engine has to establish one ring to rule them all.
The canonical definition?
Exactly. This is the single official company metric. and it's defined by a formal business document before a single line of Python is ever written.
And the canonical rule they established is this. A loan is officially in default if it is 90 days or more past due, if it has been charged off as uncollectible, or if the borrower has formally entered bankruptcy.
And that's not just made up, right?
No, that isn't just an arbitrary choice at all. It aligns with major international regulatory frameworks like Basel III and IFRS 9. Those frameworks essentially dictate how global banks measure and report risk, so adopting their standard gives the canonical metric immediate legitimacy.
But there's a massive exception to that rule, which is restructured loans. Remember, the board was treating all 957 restructured loans as permanently defaulted. The canonical definition says that if a loan was restructured, but the borrower is now performing, meaning they're currently paying on time, and are less than 90 days past due, it is not counted as a default, unless they slip up and hit that 90-day mark again.
Because a restructuring that the borrower is successfully paying off represents a problem that has been solved. Continuing to count it as a failure forever, like the board does, wildly overstates the risk in the portfolio.
Absolutely.
And the other major component of the canonical rate is that it measures gross exposure. It takes the outstanding principal balance, adds the accrued interest, and explicitly does not deduct any recovery amounts from collections.
Wait, hang on. I have to challenge that gross exposure rule.
Go for it.
If a borrower defaults on a $10,000 loan, but our collections team manages to squeeze $2,000 out of them by seizing a motorcycle or whatever, my real actual loss is only $8,000? Why would the official canonical company metric just ignore the money we literally got back? That seems like bad math.
Well, it seems counterintuitive until you separate the event from the accounting. The canonical rate is trying to answer a very specific question, which is, what percentage of our portfolio's total economic exposure is currently existing in a state of default?
Okay.
It is measuring the footprint of the failure event itself. The finance team's net loss view is answering a different question, which is, how much money did we actually lose at the end of the day?
Ah, I see the distinction.
Yeah, if you mix those two questions together, like if you shrink the default metric just because you recovered some collateral, you dilute your understanding of how many loans are actually failing in the first place.
Yeah.
You obscure the operational problem.
So what does this all mean for the boardroom? It means the engine forces everyone to agree on a foundational reality. And it uses architecture decision records, or ADRs, to document the exact logic.
Exactly.
Like why 90 days? Why gross exposure? Why the restructuring exception? It's all written down and justified. So 6 months from now, when turnover happens, no one is guessing why the code works the way it does.
And establishing that canonical number, which comes out to 22.14%, is a massive achievement. But it doesn't magically make the other teams drop their own metrics. The board is still going to walk into the meeting, look at that 22.14% and say, well, our legacy spreadsheet still says 71.70%. Prove to us why your new engine is right and our historical reporting is wrong.
And this is where the hackathon project transcends just being a calculator and becomes something brilliant. It features a reconciliation engine.
Right.
It doesn't just calculate the new 22% canonical rate, it actually replicates the 4 legacy rates perfectly alongside it, and then mathematically explains the gap between them.
If we connect this to the bigger picture, the engine achieves this by decomposing every single basis point of divergence. For context, a basis point is just 1/100th of 1%. So 100 basis points equals 1 full percentage point.
Got it.
The engine analyzes the board's number and outputs a precise explanation. It says, your metric is exactly 4,955 basis points higher than the canonical rate specifically, and only because of your permanent default rule on those 957 restructured loans.
That is so specific.
Right. And turns to the risk team and says, you are 2,704 basis points higher precisely because you use a 30-day threshold instead of 90, which alters the classification of 529 specific loans.
It's honestly like hiring a highly analytical couples therapist for the different corporate departments.
I love that.
It doesn't just sit there and say, you two disagree, figure it out. It hands them a receipt and says, you disagree specifically because of this exact parameter affecting this exact amount of money.
Exactly.
It even generates what they call exemplar loans. It outputs a markdown report that points to a specific real borrower-like loan L 2025-01839 and says, this exact loan has a DPD of 64. That is why it's flagged as defaulted for the risk team, but totally fine for the canonical rate.
And providing that level of transparency is how you build trust in a new system. And they ensure that trust is maintained by exposing this entire engine via a REST API. An API is essentially a digital waiter that allows other software, like an Excel model or a corporate dashboard, to request data from the engine.
Okay.
But they wrap this API in a Python library called Pydantic.
Pydantic sounds like someone who corrects your grammar at parties. What does it actually do here?
Well, in this context, Pydantic acts as a ruthless border guard for the data. If a financial dashboard asks the API for the default rate, but sends a badly formatted request, or asks for a threshold that doesn't make sense, Pydantic intercepts and rejects the request immediately.
Oh,
Yeah,
nice.
it prevents the system from processing bad instructions and spitting out a corrupted number. Furthermore, when the API does send a number back, it doesn't just send 22.14%. It sends a full package containing the number, the observation date, the specific thresholds used, and the exposure rules.
It gives you all the context.
Exactly. The numbers are never ever orphaned from the methodology that created them.
It's an incredibly elegant architecture, but a system this complex, trusted to reconcile tens of millions of dollars. I mean, it is incredibly dangerous if it fails quietly. Which brings us to the engine's testing philosophy.
Right.
If you want to trust a system like this, how do you ensure it's actually correct? You actively try to destroy it.
You have to move far beyond what developers call the happy path. Most standard software testing just checks if the code works when a user inputs totally normal, expected data.
Boring.
Right. Adversarial testing is the discipline of treating your test suite as an ongoing, hostile attempt to break your own system.
For example, boundary testing. The canonical rule is 90 days past due. They didn't test the engine by feeding it a loan at 50 days and a loan at 150 days. It's too easy.
Yeah.
They tested exactly 89 days, 90 days, and 91 days past due.
Yes.
It's exactly like a bouncer at a nightclub. You don't test a bouncer's ID checking skills by sending in a 50-year-old and a 10-year-old. You test them by sending in someone on the exact day of their 21st birthday and someone who is exactly 1 day shy.
That boundary is exactly where off-by-one coding errors hide. They also utilized fuzz testing. Fuzz testing involves pointing a fire hose of completely randomized, chaotic, and often contradictory inputs at the system, just to see if the underlying math shatters.
Just overwhelming it.
Yeah, they generate thousands of bizarre loan scenarios to ensure that mathematical invariants always hold true. An invariant is a rule that can never be broken. For instance, verifying that no matter how weird the data gets, the final default rate never drops below 0% and never goes above 100%.
And all this adversarial testing wasn't just some academic exercise to show off for the hackathon judges. It actually found a real bug in their logic, a critical one.
It did. The fuzz testing constructed a highly unusual scenario. It was a loan that was simultaneously flagged as restructured and charged off as uncollectible.
Oh, wow.
Remember the canonical rules. A performing restructured loan is an exception. It shouldn't be defaulted. But a charged-off loan is a total loss and must always be defaulted. When the system encountered a loan carrying both flags, the original code applied the restructured exception first, classified the loan as healthy, and completely skipped checking the charged-off status.
Wow. It just ignored a total loss because it read the wrong label first.
Yeah, and fixing that single logical flaw changed the final canonical default rate from 20.87% to 22.14%. That one tiny oversight was misclassifying $655,000 of exposure.
And what if they hadn't caught it? What if they just ran standard tests and shipped it?
That right there is why silent bugs are the most terrifying concept in financial engineering.
Well,
A bug is easy, it crashes the system, throws an error screen, and you fix it. But a silent bug runs perfectly. It completes the calculation and produces a number that looks entirely reasonable to the human eye. That technically wrong number gets submitted to the board of directors, it gets filed with federal regulators, and it corrupts multi-million-dollar capital allocation decisions for years before an auditor finally notices the discrepancy.
Here's where it gets really interesting, though. Speaking of tiny, insidious errors, even if your logic is absolutely flawless and your adversarial tests all pass, the fundamental way computer processors do math can still ruin everything.
Oh, absolutely.
This is the specific technical choice that won the project its honorable mention.
Right, so the vast majority of programming languages represent fractional numbers using something called floating point arithmetic. It's an efficient way of storing numbers in binary format, which is the native language of computer hardware.
Okay.
The problem is that most decimal fractions, the exact kind of fractions we use for human money, cannot be represented perfectly in binary.
Wait, let me stop you there. You're telling me that standard modern computers literally cannot do basic math, like 0.1 plus 0.2. How is the global banking system not collapsing as we speak?
I know it sounds completely absurd. Think of it like trying to perfectly divide a $10 bill among three people. You can hand out $3.33 to each person, but there is always that one penny left over that simply doesn't fit the math.
Right, the math doesn't close.
Standard computers do that with almost every decimal fraction. In human decimal math, zero point 0.1 is exact. In binary, it's a repeating infinite fraction. So the computer stores a very, very close approximation. If you ask standard Python to add zero point 0.1 and zero point 0.2, it does not output zero point 0.3. It outputs 0.300000000000000.
That is wild. It just hallucinates actual decimal dust.
For a single calculation, that tiny error is entirely invisible. But this engine is aggregating $51.7 million across nearly 2,000 loans. When you are summing, dividing, and multiplying thousands of balances and accrued interests, those floating point errors accumulate.
Oh, okay.
Those digital pennies turn into real missing dollars. And worse, they are non-deterministic. Depending on the specific hardware running the code or the random order the loans are processed in, the exact same inputs might produce a slightly different dollar amount on Tuesday than they did on Monday.
So how did the developers solve a flaw in the fundamental nature of computers?
By refusing to use floating point math for any monetary values, the engineer utilized Python's decimal type. The decimal library forces the computer to step away from its fast native binary math and essentially simulate human decimal arithmetic. Under the hood, 0 0.1 plus zero point 0.2 is exactly zero point 0.3.
I imagine that comes with a penalty, though. Like, it can't just be free.
It does. It is significantly slower for the processor, and it requires the developer to write much more explicit, verbose code. But the trade-off is that the math is perfectly precise and perfectly reproducible every single time.
That's a trade-off you have to make.
Yeah, and the hackathon judges explicitly called this out in their citation. They noted that this choice showed a discipline that reflects genuine understanding of floating point error in financial systems. They recognize that engineers who blindly default to floating point math without considering the context are building financial systems that are destined to fail at scale.
It proves you understand what happens when abstract code collides with the reality of money. Which brings us to the biggest takeaway of this entire deep dive. This semantic engine was built to solve a fictional fintech's default rate. But the core problem plagues every single company on Earth.
It really does.
Think about your own workplace. The word revenue means something entirely different to the sales team than it does to finance. Sales counts revenue the moment the contract is signed, but finance refuses to count it until the client's cash actually clears the bank.
It happens everywhere. Headcount means something different to HR versus payroll, or independent contractors included. What about part-time staff? A metric starts simple, it gets operationalized differently by different departments, and eventually, nobody agrees on the reality of the business.
So I challenge you to look closely at your own workplace this week. What critical numbers are you arguing about in meetings that are actually just semantic disagreements masquerading as math problems?
This raises an important question, especially right now. Every company is currently rushing to feed all of their corporate data into AI models to make automated, instantaneous decisions. But if those models are ingesting raw, unreconciled metrics, what exactly is the AI learning?
Right. Is it actually learning the fundamental reality of your business? Or is it just blindly absorbing the semantic confusion of 4 different siloed departments?
If you feed an AI a 49% default rate and a 0% default rate to describe the exact same portfolio on the exact same day, the AI has no way of knowing it's looking at an incentive conflict. It just sees contradictory data.
Exactly. If we don't build semantic engines to establish a shared reality first, deploying AI isn't going to magically fix your business. It's just going to automate your arguments.